So when you look at the spectrum of stars, you get the spectral type related to the color index. So remember, color index, the color index, which is B minus V, is related to the temperature, which is related to the spectral type. So they're all related together. And then what turns out, though, is there's an interesting relationship here with magnitudes also. We know that small stars and big stars can have different brightnesses. So if you have two stars that are the same temperature, then the small star is going to be dimmer than the big star. Now, if you have two stars that are the same size, but they're different temperatures, the hotter star is brighter. If you have two stars that are different temperatures, then it's possible the smaller star is the same brightness as the hotter star, or it's possible it's even brighter. The small star might be brighter or equal in magnitude to the big star. And so American astronomer Henry Norris Russell started studying the relationship between a star and its size and temperature. Well, he noticed an interesting thing here, and that is that the width of the spectral lines, remember Walter Adams, also an American astronomer, the width of the spectral lines turned out to be related to the absolute magnitude. And he started realizing that different stars had different properties. They noticed there was a general trend that a lot of stars that were hotter tended to have smaller absolute magnitudes, meaning brighter. Well, that means there was a trend in size. That many of them were about the same size. But he noticed that wasn't entirely the case. That there were some stars that had really big absolute magnitudes that were also really cool stars. And so he started looking at this, and another astronomer, Edgar Hertzsprung, was also studying the same phenomena. And one of them had charts and tables of data, and the other one, rather, one of them had tables of data, and one of them was making graphs. And what happened was they were both giving a presentation about the results at a meeting of the American Astronomical Society, and they realized they were both working on the same basic project. So they got together and put their work together and came up with what we call the Hertzsprung-Russell diagram. That's just long and hard to say, and so we often just call this HR diagram. And so their very first indication here was color index down here. So negative color index to the left, to the right is positive color index, and the magnitudes get bigger going down because bigger number means dimmer. So that means it's bright at the top, dim at the bottom, cool on the right, and hot on the left. And they noticed there were a few big cool stars, but most stars tended to follow like this. Well, with a little more practice, more stars, astronomers started making more Hertzsprung-Russell diagrams, and they realized that most stars, if you have the absolute magnitude, again, color index here, so 0, this is negative right here, positive this way, bigger numbers that way. That means luminosity is bigger this way, and temperature is bigger that way. Okay. I once actually presented this at a seminar up at University of North Texas, and I had my graph up there, and my graph had temperature getting bigger to the left, and the magnitudes getting bigger going down, and the department chair was saying, why did you graph it like that? Well, that's the normal way of doing it, because really it's luminosity, a brightness of star, up like this, and B minus V getting brighter like that. So that's really the normal way you do it. Well, most stars turned out to be in this diagonal strip across the HR diagram. And we call that the main sequence. Now, these stars up here are the same temperature as stars down here, but they're obviously much brighter. And so they are much, much larger, so we call these giant stars up here. Okay. The Hipparchus spacecraft measuring parallax also measured the brightness of the stars, figure out the absolute magnitude if you know the distance, and so this is an HR diagram of the Hipparchus stars. Most stars are in the main sequence. Okay. Now, the interesting thing is that as you go down here, that these stars are very, very dim and very hard to see. When you go out and look at stars, the stars that you see are typically these stars because they're the bright ones you see in the sky. Okay, they're not really the most common kind of stars. Most stars are like that. Now, there are a very small number of stars in the lower left. They are white hot, but they're way smaller than other stars because they're way dimmer, way smaller than other stars, the same basic temperature, and so we call those white dwarf stars. Okay. Only a small percentage of stars are up here. Most stars are on the main sequence. 90% of all stars are on the main sequence. But the stars you see in the sky are either these stars here or these up here. And so that means you see a huge number of these red giant stars, even though they're very rare. Now, this is in astronomy something that we call the Malmquist bias. After astronomer Malmquist. Basically, he says what you see is not necessarily the most common thing. What you see is the thing that stands out. And so this is actually true in a great many situations that the pretty common things, if they're just kind of going under the radar, you don't notice them. It's just the one or two odd things that really catch your attention. You see not the most common kind of star, you see the ones that stand out. It's like going to the forest. You say, well, what do you see in the forest? You see trees. What's the most common thing in the forest? Well, it's not trees. Okay. There's way more bushes than trees. There's way more birds than there are bushes and trees. There's way more bugs than there are birds. And so really the small things that are hard to see are the things that are most common that are in the forest. What you see are the big, easy to see things, the trees. And so same with stars. The stars you see are the big and easy to see stars, not necessarily the most common kind of star. So again, this is an HR diagram here plotted, and the sun, interestingly enough, is right near the middle of the HR diagram. And so that's why we sometimes say the sun's kind of an ordinary star, is that there are stars that are hotter and cooler on the HR diagram. There are stars up here bigger and stars down here that are smaller than the sun. And so it's just kind of midway between the extremes.